Okay, so we're going to continue with circuits or the el- el electric potential diagrams. And again, the requirement for a circuit, you need an energy supply. We've been talking about batteries as an electrochemical cells, but energy supply can come from your power company. When your power company decide to give you power or
Yes,
energy,
the
when they decide to give you energy or power, what they do is provide you with electric potential difference. Okay, they're gonna they're gonna what they do is they will give you the ability to move your positive charge to the high potential terminal, and then the electric what the external circuit in your house, the wiring and stuff like that, will will let the electric energy travel and supply the different devices that you have attached to your circuit. Okay. Uh, so again, for the requirement for a circuit, you need energy supply, and you need a closed conducting loop in the external circuit. Okay, so that's very important. So okay, so all right, let's look at a number of questions and see. So if an electric circuit could be compared to a water circuit in a water park, okay? So all right, so if let's try and understand the question. If an electric circuit could be compared to a water circuit at a water park, then the battery would be analogous to, we say that the battery, okay, so what the battery does in the electric circuit, it pumps the positive charge to the positive terminal, to the high potential terminal. So so at the water park, the water pump, the water pump is going to move the water from the ground level up to a high position. And once the water is in the high position, it can run down. Okay. The positive terminal of the battery would be analogous to the top of the slide. So that's where you're going to put the water, the top of the water slide. So the positive terminal, which is the high potential terminal, is equivalent to the top of the water slide. The current would be analogous to what? What would be the current? Remember what we say. Current, well, we haven't said it yet, but the definition for current, the definition for electric current is the quantity of charge per unit time. So current, which we're going to discuss in a little bit more detail. So current, and the symbol for current is I. So I current is equal to the quantity of charge passing a point. Okay, the quantity of charge passing a point per unit time. So it is charge, that's a C, per time. Okay, so current is charge per time. The definition for current, it is the quantity of charge passing a point per unit time. So what is equivalent to that? It is the gallons of water flowing down the slide per minute. This is what is equivalent to the current. Okay? Quantity of charge passing a point per unit time or per second, whatever. So that's equivalent to the gallon of water flowing down the slide per minute. That is equivalent to the current. The charge would be analogous to the water. The water it would be analogous to the charge because it's the water which is moving and it's the charge which is moving. So the water moves down the water slide in the water park, and the charge moves around the wire in the electric circuit. The electric potential difference would be analogous to, so is the water pressure. So the water pressure is analogous to the electric potential difference. Okay, so all right, let's look at the next question. So you have to get those concepts clear. Those things have to be very clear in your mind. Okay, so your roller coaster, your water in your water park is similar to the electric current electricity. You know, with current electricity, you have what we call a potential difference. The potential difference is nothing more than potential energy. So you give the charge potential energy, and then once you release the charge, that potential energy is converted into electric energy. And that electric energy, once it moves around the circuit, can be converted to light energy, motor energy, sound energy, you name it. Okay? We just use the electric energy to convert we transform it into other energy. Okay? All right, so let's look at question 2. All right, so utilize your understanding of the requirements for an electric circuit to state whether charge would flow through the following arrangements of cells, bulbs, wire, and switches. If there is no charge flow, then explain why. So, the requirement for a circuit, you need a complete loop in the external circuit, and you need an energy source, energy supply. So look at A. All right, so we have our battery, we have our energy source there. We have this is a conductor. Then we have a bulb, and then, so this circuit is complete. Okay, but let's see. All right, the circuit is complete. So are you going to have charge flowing, yes or no? So, okay, so the battery source is going to provide the electric potential difference, or the potential energy. So the battery is going to provide the potential energy. Okay, and this potential energy is now going to be converted to electric energy. What the battery does, it's going to move your positive charge from the negative terminal to the positive terminal. So it's going to move it from the low potential terminal to the high potential terminal. Then once you have a complete circuit, the positive charge is going to flow through the circuit. So the only problem with this is that the switch is not closed. This switch is not closed. This is a nice circuit, but the switch is not closed. In order for the charge to flow continuously, you need to close the switch. So if this switch was closed, no problem. Let's look at B. You have your battery, electrical potential difference. You have a closed loop right there. You have the battery on top. There's no potential difference, because in order for charge to flow, you have to connect your low potential terminal to the high potential terminal. There is no connection there, so nothing gonna flow there. Okay, let's look at this one. We connect our low potential terminal to the high potential terminal, but the battery is on top of the high potential terminal. This is not a closed loop, so you're not gonna get the battery is not the bulb is not gonna light. Let's look at this one. Okay, you have two batteries there. The positives and then the negative. So in this case, you may get the bulb light and the bulb may light, and but the only if you look at this, you can say it's a complete circuit. But if the batteries are of the same voltage, there's no electric potential difference. The batteries have to be of different voltage. Then you'll get electric potential difference. Then charge will flow. So in this case, you may get flow. Okay. So none of these. Only this one. If you close the switch, you'll get charge flowing. All right. Let's look at the diagram. This diagram. The diagram at the right shows a light bulb connected to a 12 volts car battery. The positive and the negative terminals are shown. Okay. As a positive charge moves through the battery from D to A. So the positive charge. So remember, all the battery is going to do is the battery is going to move the positive charge from D, the low potential terminal, to the high potential terminal. You need energy for that. You need energy because you're moving a positive charge towards a positive charge. You need energy for that. And that's what's going to create the electric potential difference. Okay? Okay. So as a charge moves through the battery from D to A, so it's going to move from D to A, it gain or lose potential energy. Remember what we said. It's going to gain potential energy. You're moving the charge from the low potential terminal to the high potential terminal. All you're doing is giving it potential energy. Once you give it the potential energy, then that potential energy is going to move through the circuit as electric energy. It is similar to the water park. When you raise the water to the top of the slide, you're giving it potential energy. This is the same thing. So it's going to gain. So the charge is going to gain potential energy. And it's going to, so if it's gain potential energy, it's going to gain electric potential energy. So those things are interchangeable. When it gains electric potential, it actually gains electric potential energy. Okay? The point of highest energy within the battery is the positive terminal. Remember, we said the positive terminal is the high potential terminal. So that's the point of highest energy within the battery. As a positive charge moves through the external circuit from A to D. So once we move the positive charge from the low potential terminal to the high potential terminal, we have to do nothing more. Naturally, once you connect the circuit, the charge is going to flow from the positive, from the high potential terminal, positive terminal, through the circuit, external circuit now. It's going to light up the bulb, and then it's going to come back to the low potential terminal. So as the charge moves through the external circuit from A to D, as the charge moves, it's gain or lose. Remember, it's going to lose potential energy. Okay? It's going to lose potential energy because the potential energy that is right here is going to be converted to electric energy. Electric energy is going to flow through the wire. It's going to light up the bulb. So some of that electric energy is going to be converted to light energy. So it's going to use up some of the energy. So it's going to lose energy. Okay? So as it moves from A to D, it lose potential energy and it lose electric potential. So, it's going to lose energy because that's what it's supposed to do. When when the charge, the positive charge, flows around or moves around the circuit, okay, it's actually electric energy, and that electric energy is going to be converted to other type of energy. So the electric energy is going to get less. So it's going to lose electric energy. It's going to lose electric potential energy. Okay? The point of highest energy within the external circuit is, so the point of highest, is A, right? So the point of highest energy within the external circuit is closest to A, right? Because this is the highest electric energy, the highest electric potential, the highest electric potential energy. And then once it moves through, it's going to lose energy. So the closest to the positive terminal is going to have that. Okay? All right. And then, you can do the rest. All right. All right. So we look at current. All right. So I gave you a brief description of current. When we say current, current is the flow of charge. You cannot have current if charge is not flowing. And remember what we said at the water park, the current is analogous to the flow of water in the water park. So current is just a flow of charge. The proper definition for current is the rate at which charge flows past a point on a circuit. Okay? That is the quantity of charge Q passing through a cross section of a wire every second. So it is the quantity of charge that passes a point every second. So we the current is, the unit of current is the ampere. So 1 ampere is equal to 1 coulomb per 1 second. The quantity of charge that passes a point every second. The unit of current is ampere. Okay? The unit of current is the ampere. We abbreviate it as amp. So that is the metric unit. Ampere, we abbreviate it as amp. But 1 amp is really 1 coulomb every second. That is the amount of charge that passes in every second, 1 coulomb. Again, the current I is equal to the quantity of charge C per unit time. So it is charge per time. So the ampere or the amp is same as coulomb per second. We alluded to this before. When you look in a circuit, we talk about by convention. So by convention, when we talk about current flowing in a circuit, it is the positive charge which is moving from the high potential terminal to the low potential terminal. That is what the current is. However, the electrons actually move in the opposite direction. The electrons are going to move from the negative terminal to the positive terminal. The electrons move in the opposite direction. But just by convention, international convention, okay, by international convention, the positive charge moves from the high potential terminal, positive terminal, to the low potential terminal. Okay? But the electrons move in the opposite direction. Okay? Again, the current is directed from the positive terminal towards the negative terminal. The electrons actually move in the opposite direction. When we did static electricity, we introduced the concept of electric field. Once you have a charge anywhere, it's going to set up an electric field. And when it set up that electric field, of course, when we drew the field diagrams, if you have a positive source charge or from the positive terminal, the electric field lines are going to move away from the positive terminal. So you need to remember the electric field and what it represents, because we're going to come back to that. All right. Okay, so this, you have a battery. You have a positive terminal, a negative terminal. Positive terminal is the high potential terminal. The negative terminal is a low potential terminal. The battery, all the battery does, it's going to move the positive charge to the positive terminal. And by convention, the current is going to flow from the positive terminal to the negative terminal. But the electrons actually flow in the opposite direction. The electrons are going to flow from the negative terminal to the positive terminal. Okay? Remember that. Remember what current is. Current is the quantity of charge that's flowing across a point per unit time. The quantity of charge per time, or charge per time. Okay? Okay, let me not introduce that concept yet. All right, let me introduce that concept. All right, so when you turn say you turn your light switch on, instantaneous light comes on. You don't have to wait until the electron travels from the negative terminal to the positive. You don't have to wait for that. Okay? You don't have to wait for that. Okay? The electron's going to move from the negative terminal. Sorry about that. So the electrons are going to move from the negative terminal to the positive terminal. The current, by definition, is going to move from the positive terminal to the negative terminal. Say we have, say the wire is a copper wire, or copper wire. When the electrons are moving, the electrons move in a very haphazard, zigzag fashion. Okay, the electrons are gonna move in an haphazard, zigzag pattern. The electrons, when they travel, so the electrons are gonna collide with atoms, and when they collide with atoms, they're gonna bounce all over the place. So it's not that when you complete your circuit, when you put your switch on, it's not that you're gonna have electrons flowing smoothly all the way around. No, because in the wire you're gonna have atoms, and the electrons are gonna collide with these atoms. So it's not gonna have a nice straightforward path. It's gonna be it's gonna have a zigzag. It's gonna have a zigzag motion. Okay, so it's gonna bounce this way. It's gonna bounce this way. It's gonna bounce this way. So the electrons are gonna have a very haphazard zigzag motion because they're gonna collide. they're gonna collide with they're gonna collide with atoms, and the direction is gonna change. Okay. However, once you complete the circuit and you have your potential difference, the electrons are gonna travel this. They they're gonna have a net direction going this way. Okay. But it's not going to be a smooth ride. They're going to bounce all over the place. They're eventually going to come all the way around, but they're going to move very slow, very slow. Electrons are move extremely slow. Okay? The electrons move very, very slow because they're colliding with atoms and they're going to change their directions. Okay? We call that drift. So now we introduce the concept of sorry, we introduce the concept of drift speed or drift velocity. So when we talk about drift speed or drift velocity, it's the average distance traveled by a charge carrier per unit time, which is the electron. The average distance traveled by a charge carrier, i.e. the electrons, per unit time. Okay? The overall drift speed for an electron in a circuit is about 1 meter per hour. Think about it. Every hour, all the distance the electron travel is just 1 meter. However, when you turn your your light switch on, you get light instantaneously. You get light right away. The reason for that is because you have electrons all throughout your external circuit, right? So you're not waiting for the electrons from the high potential terminal to now travel to you're not waiting for that. Electrons are all throughout the terminal. So once you turn your light switch on, electric field is almost instantaneous. It is the electric field that is established that's going to cause the electrons to move. But it's going to cause, there's a chain of electron all around the circuit. So it's gonna induce the electrons to move. Okay? The average speed of the electrons are very, very slow. Think about it in terms of the water in your pipe. When you turn the water on, say you're gonna get a shower. When you turn the water on, the water comes on instantaneously. You're not waiting for the water from the source to come to you. That is because water is continuously in the pipe. Water is in the pipe. So when you turn your tap on, water from the source is going to move forward, but the water already in the top of the top is going to come out, and that's similar to your electric current. The average speed of the electrons are very slow. We call that the drift speed, which is the distance traveled by the charge carrier, that is the electrons. But when you turn your switch on, the electric field is almost the speed of the electric field is very similar to the speed of light. The speed of the electric field is almost is very similar to the speed of light. So once you turn your electric switch on, light comes on instantaneously. That's because the electric field that is established cause the electrons to start moving, and the electrons in the front, they're going to supply their current, and then the ones behind will come up and supply their current, and that's how it works, similar to the water in the pipe. So again, when we talk about drift speed, these black arrows are your electrons, and then these are your atoms. So you see, when they come, they collide and change their direction, and so the movement is very haphazard. But the net is that they're moving in this direction. They're moving from left to right. Okay, but they bounce all over the place, but they're gonna move from left to right. Okay, again, when you establish uh, an electric circuit, you get an electric field, which is usually in the opposite direction to the electrons. The electric field is almost instantaneous. So the electric field signal travels at nearly the speed of light. So again, when you turn your light switch on, electric field comes up right away, and it causes the electrons to start moving. The electric field is almost nearly the speed of light, and that's what's going to cause the electrons to start moving. And then, the electrons closest to the light source is going to light up the light source, and then the ones behind going to come up, just like you have the water in your tap. So the electrons get the signal at the same time. All the electrons get the signal at the same time, because the electric field signal is almost instantaneous. Again, the electrons move in a zigzag pattern, but they're going to move in the direction that they're supposed to move. Okay? The rate at which charge enters the external, this is another important point. The rate at which charge enters the external circuit at one end is the same as at which it exits the circuit at the other end. So what we're saying, the rate of charge, once they say rate of charge, that's current. Remember, current is the current is the quantity of charge per unit time. Rate, the charge per time. So the rate at which charge enters the external circuit at one end is the same as which it exits at the other end. What we're saying is that the current going in is going to equal to the current going out. Okay? So the current everywhere is the same, and this is what we mean. So if you look at this circuit, this is your battery. Okay? So this is your battery right here. Low potential terminal 0, high potential terminal 12. Your current is going to move from the high potential terminal to the low potential terminal. So the current here is 8 amperes or 8 amps. Okay? When it comes here, it probably split to 2 amps, but the current all along here is going to be 2 amps. And then when it comes, so 6 amps is going to come here. Everything down here is going to be 6. Okay? 6. And then the 6 and 2 going to combine. So what we're saying is that the current leaving or exiting the external circuit is going to be equal to the current entering. Okay? And we'll come later on to parallel circuits and series circuits. But if it's 8 right there and it splits into 2 and 6, these 2 and 6 are going to combine. So when it enters, it's going to enter as 8. Okay? We'll come back to that later on. And then this is a simple circuit, a series circuit. So if it leaves at 1.5 amps, everywhere along here, the current is going to be the same. And when it enters the battery or the negative terminal, it's also going to be 1.5 amps. Current everywhere is going to be the same. So we're going to stop here, and then later on we're going to discuss circuits, and we're going to put more things into the circuit. We're going to put in the switch, we're going to put in some device in the circuit, we're going to look at parallel circuits, we're going to look at circuits in series, and we're going to get a little bit more complex.